Now we have a fundamental theorem. So it says that for any square matrix A of order n, the following are equivalent. So the first statement is A is invertible. The second means equivalently, the Rouse echelon form of A is the identity matrix In, which we have already proven. So we know that if A is invertible, so the Rouse echelon form of A is identity matrix. This we already know. What's new here? The new thing is that the determinant of A is not equal to 0 and the rank of A is equal to n. So this can be seen through an example. I will do it later. There is a corollary. Corollary is just based on this theorem. It says that if A is not invertible, just flip the whole of this statement. If A is not invertible, then again the following are equivalent. So the first one is that its row echelon form has at least one zero row. Since previously we were supposed that A is non-singular, in other words, A is invertible, but here we are saying that A is non-invertible. So the previously when we were talking about the invertible A, we were saying that the row echelon form of A was identity matrix. So identity matrix is the matrix in which there is no zero row. But here the row echelon form of A must have at least one zero row because A is non-invertible. Another way to say the same thing is that the determinant of A is 0, and another way of this is to say that rank of A is less than n. In other words, rank of A is not equal to n. So this is the corollary. So these are alternative statements which are equivalent. That means if the rank is not equal to n, then the determinant is not equal to determinant is 0 and the matrix is not invertible. And also the row echelon form of the matrix has at least one zero row. The whole row is 1. The whole row is 0. At least there is one row which is 0. Okay, let's do an example. There is an exercise. In this exercise, we are given that the matrix is not invertible. We have to find the lambda. Okay, since we are given that the matrix is not invertible, that means the determinant of A is 0. Whenever the matrix is not invertible, the determinant will always be 0. So let's solve this example. We will use the fact that it is not invertible, so the determinant is 0. First of all, we will compute the determinant. Then we will put the determinant to be 0 because it is not invertible. So what is the determinant of this matrix? So if we compute the determinant along the first row, you can check the first row has 1, 3 and 2. So I have put 1, 3 and 2. Then multiply -1 everywhere. You can check. Time the power of this -1 is 1 plus 1 because this 1 is in the first row and the first column. But this 3 is in the first row and the second column. So I will write 1 plus 2. And this 2 is in the first row and the third column, so I will write its power to be 1 plus 3. And we will write the determinant of the submatrices. You can check how I have written this, how I have written this, how I have written this. Very easily, whenever you are doing with 1, I will ignore this column and this row, and I will write this determinant. Understand? And similarly, if I am doing with this entry, I will ignore this, I will ignore this. I will write this determinant, which is lambda 5, 7, 8. You can check lambda 5, 7, 8 here. And similarly for this, I will ignore this column in this row. This is the submatrix which I have written here. Now I will calculate all of these things. After simplifications, I will write these things, and after more simplifications, these two terms will be 3, and if I multiply 3 inside, I will get these two terms. If I multiply 2 inside, I will get these two terms. Okay, if I add these two terms, I will end up with negative 6 lambda, and if I add these three terms, then I will get 24. Since it is given that A is not invertible, and from the corollary we know that if A is not invertible, then the determinant is 0. Since this is the determinant of the matrix and the matrix is not invertible, so that means this determinant is 0. So I will put this is equal to 0. Hence, this entry is equal to 0. From here, I can take this 6 lambda to the other side. So 6 lambda is equal to 24. And I can divide both sides by 6. So I will end up with lambda to be 4.